Hello everyone. So today we'll be talking about sets. So a set can be anything. You can have a set of books, a set of cars, basically any collection of objects can be a set. So what is a set? A set is a well-defined collection of distinct objects. So any object, it can be a set of numbers, a set of letters, anything. Things or objects that belong in a set are called elements. So if you have a set of numbers from 1 to 3, 1 would be an element since it's an object in that set. So another example of a set would be the set of prime numbers between 1 to 10. This could be represented as P is equal to 2, 3, 5, and 7, as these are the prime numbers between 1 and 10. Sets are usually denoted by capital letters. So if you have a set A is equal to 1, 2, 3, the A there would always be in capital. Now let's proceed to set notation. So as we know, objects in a set are called elements. So in the set A is equal to 2, 5, 7, 2 is an element of the set since it's an object in it. Likewise, 5 is an element and 7 is also an element. This can be denoted as 2 is a member of A. So that symbol represents belongs to or is a member of, and it symbolizes that 2 is an element of set A. So as a result, we can conclude if X can be anything, if X is an element of A, then we say X belongs to A, or we put it in terms of the symbol, X is a member of set A. That's what the E-like symbol represents. Likewise, if X is not an element of A, then we say X does not belong to A, or X is not a member of set A. So that's why we have a cross over the E-like symbol. A set without any element is known as an empty set or null set. So an example of a null set would probably be like the number of even numbers less than 1. There's no even numbers less than 1, so that is an empty set. Another example would be a set of even prime numbers greater than 3. All even numbers are multiples of 2, so they cannot be prime. So as a result, that would also be a null set. So a null set is represented by the symbol phi, and we can express it as phi is equal to open brackets, a blank space, and close brackets. So here are some problems which we can look at using the knowledge we have developed so far. So suppose B represents a set of integers from 11 to 15. How would we represent B in set notation or roster form? Roster form is how we represented the set before. Okay. So here's how we represent it. B is equal to 11, 12, 13, 14, and 15 in brackets. Let's go on to another question. Express the relationship between 12 and B using notation. So if we look at it, we can see 12 is between 11 and 15. So, and 12 is a part of set B. So as a result, we can see 12 is an element in set B. So if we express it through notation, that would be 12 is a member of set B. Now we have to express the relationship between 20 and B using notation. If we look at set B, 20 is not between 11 and 15. So it is not a member of set B, or it's not an element in set B. Therefore, using notation, we can represent 20 as 20 is not a member of set B. Now let us look at unions. So let A be a set with elements A, B, and C, and let B be a set with elements D, E, and F. So what would be the set of all the elements in A and B? So if we look at it, a set of all the elements in A and B would basically be combining the elements in A and the elements in B. So this set would then be A, B, C, D, E, and F. So now we've basically combined all the elements of set A and B into one set. And this can be represented as A union B. The union is shown by that symbol which looks like a U. So therefore we can say A union B is equal to A, B, C, D, E, and F. So since we know this, we can say if X is a member of A union B, X is a member of A, or X is a member of B. So we know A union B consists of all the elements in A and B. So suppose X is an object and it's a member of A union B. X can be a member of set A, and it would still be a member of set A union B, or it can be a member of set B, and it would still be a member of set A union B. Or it's even possible for X to be a member of both sets, since A union B consists of all the elements that are present in A and B. Likewise, we can say if X is not a member of A union B, X is not an element of A and X is not an element of B. Oh yeah, that's meant to be a union sign. So yeah. So here is a diagram of A union B. As we can see, the circle on the left represents set A and the circle on the left represents set B. So A union B would mean to shade everything, the entire area of set A and the entire area of set B, because it consists of all the elements in set A and set B. Now let's move on to intersections. So let's set A be A, B, and C, and let's set B be B, C, and D. What is the set of all elements in common in A and B? So let's look at it. So in set A we have elements A, B, and C, and in set B we have elements B, C, and D. So I can see a B and C. There's no A in set B and there's no D in set A. So B and C are the elements which are in common in both A and B. So therefore, this set would then be B, comma C. So we can then denote this set as A intersection B. So the intersection sign is basically an upside down U. So hence we can state A intersection B is equal to B, comma C. Therefore, if X is a member of A intersection B, X is a member of both A and X is a member of both B. Now if we compare this with unions, if X was a member of A union B, X could have been a member of either A or it could have been a member of either B. But in terms of intersection, if X is a member of A intersection B, we're basically saying that X is an element which is common in both A and B. So it has to be a member of both A and B. So here is a graphical representation of A intersection B. So we can see that the shared areas between A and B represents the intersection, or like the overlapping bit, because that is the area they both have in common, right? Thank you guys for watching the video. Next week there'll be more on sets to come.